Good day, students. Welcome to math.serve.com. In this clip, we're going to be going over problems 6 to 10 of the June 2016 Algebra 2 Common Core New York Regents exam. If you have any questions at any point in time during this presentation, feel free to post your questions in the comment section below, and we'll be more than glad to support you. All right, let's take a look at question number 6. It reads, the zeros for f of x equals x to the fourth minus 4x to the third minus 9x squared plus 36x are. Now, what's the best approach to solve this problem? Now, when you're solving a polynomial for the zeros and you look at the nature of the solutions, you can tell what method to use, okay? If you notice, we have integer solutions. Whenever your solutions to the zeros of a polynomial or the zeros of a polynomial are rational numbers, then in most cases you can factor the polynomial function. So we're going to be using our factorization skills to solve this problem, okay? Now we have the following polynomial, x to the fourth minus 4x to the third minus 9x squared plus 36x. We're asked to find the zeros, so all you're going to do whenever you're asked to find the zeros of a polynomial is to set the value of the polynomial equal to what? You set it equal to 0, okay? What you're looking for are the x-intercepts. So we're going to solve by factoring as indicated earlier. Now this is a polynomial in 4 terms. Now this is a quick tip that you want to keep in mind. Whenever you're solving polynomial equations involving 4 terms by factoring, one of the best methods to try first is factoring by grouping. Okay, that should be your first approach. And if that doesn't work, then you can use another approach. Before I factor by grouping, I need to examine all 4 terms to see if there's a greatest common factor that I can extract first before I proceed to factor by grouping. Now what you notice is that x is common in all 4 terms. Okay, that's the GCF, so we can pull out an x. And then we're going to divide every single term by x to the first power. So this becomes x to the third minus 4x squared minus 9x plus 36, okay, equals 0. Now we're going to proceed to factor by grouping. Now what do I mean by factor by grouping? Well, what you're going to do is you're going to group the number of polynomials, you're going to split them into 2 equal halves, okay? So we have four terms here, so we're going to split it down the center. 2 terms to the left, 2 terms to the right, but be careful to split it right in front of the sign of the third term, okay? Because this sign goes with these 2 terms. All right, now we have the split. We're now going to consider them in pairs and extract the GCF of the terms and the 2 terms to the left and the GCF of the 2 terms to the right. Let's go ahead and do that. Bring down this x, bracket, x to the third minus 4x squared. The GCF in this case is x to the second power. Okay, now as though we divided these 2 by x squared, so we're left with x minus 4. Okay, now this part is a little bit technical. If you're looking for the GCF, you also have to extract minus because it's in front here, okay? The GCF of 9x and 36x is 9 because 9 goes into 36 4 times. So I'm going to factor out negative 9. Whenever you distribute a negative, the signs change, right? But guess what? When you factor out a negative, the signs change also. So we're going to be left with x minus 4, and then you close that, equals 0. Now, a nice thing about the factoring by grouping algorithm is that it's possible for you to check the accuracy of your factorization process. Now, here is a good place to pause and check. If you factored correctly, guess what? The terms, the quantities in the parentheses should be identical. If not, then factoring by grouping is not going to work, or you made a mistake somewhere, okay? In this case, it's identical, so we know that factoring by grouping is going to work, and we did not make any mistakes. All right, so next thing we're going to do is we're going to factor out these common terms, okay? x minus 4 and x minus 4 are common in both sides of my partition, so that means I'm going to factor it out. Bring down this x, we have x times these two common factors, x minus 4. Then what's left on the outside, x squared and negative 9. What do you do with those? You group them up in their own parentheses. All right, set it equal to 0. Now, do you recall the difference of squares factorization formula? Well, you have it right here. A squared minus b squared factors into a minus b times a plus b. Okay, so the way you do it is you root the first term and the last term, and then you express the roots as a sum and a difference. So that's exactly what we are going to do right here. We're going to root the first and the second term and express it as a sum and a difference. Okay, so we're going to have x times x minus 4, so square root plus minus. We're going to have x minus 3 times x plus 3 equals 0. Now the next thing we're going to use is the zero product property, okay? So we're simply going to set every factor equal to 0 since the product of the factors is equal to 0. So x equals 0, x minus 4 equals 0, x minus 3 equals 0, and x plus 3 equals 0. Now, the first one is already in its solved state. X equals 0. Here we just add 4 to both sides. And that gives us x equals 4. And this one right here, you add 3 to both sides. And you end up with x equals 3. Last but not the least, you subtract 3 from both sides. And then you end up with x equals negative 3. Okay, so what are our zeros? Our zeros are, if you want to organize it in the way that was presented in the options, we have 0 plus or minus 3, just to group those two together, and positive 4. The answer to question number 6 is option number 1. Okay, so there goes our final answer. All right, let's take a look at question number 7. It reads, Anne has a coin. She does not know if it is a fair coin. She flipped the coin 100 times and obtained 73 heads and 27 tails. She ran a computer simulation of 200 samples of 100 fair coin flips. The output of the proportion of heads is shown below. So we have the samples 200, the mean 0.497, standard deviation 0.05. Question. Given the results of her coin flips and of her computer simulation, which statement is most accurate? Okay, so in order to easily answer this question, we have to think about what a fair coin means. What does it mean for a coin to be fair? Well, something to note is that if you toss a fair coin a lot of times, like for example, she tossed it 100 times, a pattern should emerge. The proportion of heads compared to the entire number of tosses should be close to 50%, and the proportion of tails should be close to 50%. Okay, so a fair coin is one that the ratio of heads to tails when you toss it is close to 50%, 1/2 or 0.5. So you have a fair chance of getting a head or a tail. If you have a situation where you have more than 50% of any one of them, then the coin is not fair or is biased towards that direction, either head or tail. Okay, so if we look at what happened with her, she's not sure if this result represents the outputs or outcomes for a fair coin. So in order to help us answer the question, let's look at what the computer simulation does. Okay, remember the computer simulation is fair, all right? So how do we know that the computer simulation is fair? Because after carrying out our flips with 200 samples, the mean was what? The mean of because she's looking at the proportion of heads, okay? Out of the tosses, heads or tails, what proportion is the head? You notice that the mean is 0.497. If you round it to the 10th place is approximately 0.5, okay, or 50% or 1/2. So what does this tell us about the computer simulation? The computer, the coins that the computer simulated with is fair, okay? So the computer simulation is fair because of the proportion is so close to 1/2, okay? But let's take a look at Anne's scenario, 73 and 27. Does this look fair to you? Well, let's take a look. Let's determine the ratio, okay? So for Anne's coins, Anne's coin, we have the ratio of heads, proportion of heads, is basically 73 over 100. Okay, that's in percentage form is 0.73. Now you see what's happening here. This is not close to 1/2. This coin, her coin, is not fair. Is biased. Is biased in what direction? Is biased in the direction of the head. So whenever she flips, she's more likely to get heads. So that's not fair. Okay. So Anne's coin is not fair. All right, so if you look at the options that we have right here, it says 73 of the computer's next 100 coin flips will be heads. That's not what, that's unpredictable, okay? You can't really see exactly what the outcome of an experiment is going to be. You can just guess you can make an educated guess as to the likely outcome, not the exact outcome, okay? 50 of our next 100 coin flips will be heads. This is very unlikely, again, because the coin flip is biased to begin with, and secondly, you cannot predict exactly what the outcome of an experiment is going to be until you're done with it. Option 3, her coin is not fair. Absolutely. It's skewed in the head direction because after 100 flips, her result was not close to 50-50. Okay, if it was close to 50-50, then her coin would be fair. But in this case, it is not fair because she had 0.73, 73% was heads. That's way too much. Okay, so eliminate option 1, 2, and 4. The correct answer for number 7 is 3. All right, let's take a look at question number 8. It reads, if g of c equals 1 minus c squared and m of c is equal to c plus 1, then which statement is not true? Okay, so be careful here. We're looking for the one that's false. All right, let's try the first one. Is it true or false? Option 1, we have the product of the two functions, g of c times m of c. So we're just going to multiply these two, okay? So g of c is 1 minus c squared, and m of c is c plus 1. So we're just going to follow this out since we're multiplying two binomials. First, let's do that again. So first, outer, inner, last. Okay, that's how you expand the product of two binomials. It just helps you stay organized. All right, so 1 times c is c, 1 times 1 is 1. Now c squared has a negative, so we're going to carry the negative while multiplying. So we have negative c to the third minus c squared. All right, if we rearrange terms, so it's consistent with the option here, we have 1 plus c minus c squared minus c to the third. No like terms to be combined here. This is the final result. Option 1 is true. All right, let's move on to option 2. Option 2, we're finding the sum of the two functions, g of c plus m of c. So we have g of c, what is it? Is 1 minus c squared plus m of c is c plus 1. Now, when you're substituting, please be careful. Okay, make sure you're substituting the right expression for the right function. All right, now we're adding, we have like terms here, the constants are like terms, so we can combine them into one. So we have 2 plus c minus c squared. Option 2 is true, that's a true statement. Let's move on to option 3. For option 3, we are looking at a difference. So for 3, we have g of m of, actually switched it around now, m of c minus g of c, okay? So you gotta be careful, make sure that you're following the exact instructions here. If you notice the first two, g of c was first, and then here they switched it around, so you gotta be careful. Now, caution concerning subtracting polynomials. Whenever you're subtracting polynomials that has multiple terms, more than one, you always want to use parentheses. Okay, that helps you remember to distribute the sign, the negative sign that's in front of the parentheses or the quantity to your right. So let's do that here. So m of c is c plus 1, and then minus parentheses g of c, 1 minus c squared. Okay, so this is what I was talking about. Whenever you're subtracting the polynomial to the right, after the minus, put a parenthesis there. Good practice, and it also remembers. It also helps you to remember to do what? To distribute that sign to those two terms in the parentheses. Okay, common mistake a lot of students make. All right, so let's go ahead and distribute. We have c plus 1 minus 1 plus c squared. Like terms, yes. 1 and negative 1 are constants. They're like terms. We can combine those two. They add up to 0. We're left with c plus c squared. So option 3 is true. Now the last one is option 4. Option 4 is the quotient of two functions. So we're looking at m of c divided by g of c. So m of c is c plus 1. And g of c is 1 minus c squared. All right, if you look at the denominator, that's a difference of squares. We talked about that earlier. We said if you have a squared minus b squared, this can be factored into this product, the sum and the difference, the product of the sum and the difference of the square root of these two terms. Okay, so a plus b times a minus b. So we can apply the same procedure here. The numerator stays unchanged at c plus 1. So what you do is you root the first and second terms, and then you have a plus and minus. All right, so we have 1 minus c times 1 plus c. Now, does addition commute? The answer is yes. It doesn't matter when you're the order when you're adding, but how about subtraction? Subtraction does not commute, okay? So we may not switch the order of this except we introduce that negative sign there. So we have 1 minus c, and this 1 plus c can be switched around to c plus 1 because addition commutes. Now what happens? Divide this to 1, that goes to 1. The final answer of m of c divided by g of c is 1 divided by 1 plus c. Now, is that what we have for option 4? The answer is no. There's a minus there, and the denominator is not reversed, so it's not the same as this. Option 4 is false. This is what we're looking for. Our answer to question number 8 is 4. All right, let's take a look at question 9. It reads, the height of women in the United States are normally distributed with a mean of 64 inches and a standard deviation of 2.75. The percent of women whose heights are between 64 and 69.5 inches to the nearest whole percent is. So I gave you a normal curve. Okay, so let's just say this is a graphical representation of a situation. So it's normally distributed, so we can represent it using a normal curve. So the mean is 64. Okay. 69.5, let's just put it somewhere here. Should be somewhere here. And There goes the upper bound. What this question is asking is what percentage of the population is represented in this region right here. All right. So there are multiple functions in your calculator, but the one that is applicable to this particular problem is the normal cumulative density function. Okay. So remember what the normal cumulative density function in your calculator does. What it does is it returns the percentage of the area under a continuous distribution curve. Okay, so if you have a normal curve and you want the percentage of the area within two boundaries, you use your normal cumulative density function in your calculator. All right. Okay, so that's what we're going to use. But before we use it, let's go over the syntax. All right, so how do you tell your calculator what to do? Syntax for the normal cumulative density function is as follows. You enter the lower bound goes first. Guess what comes next? The upper bound, and then you enter the mean, and lastly you enter your standard deviation. If you look at the problem, these values are nicely provided for you. Okay, so what we're going to enter in our calculator is normal CDF. The lower bound is 64. The upper bound is 69.5. The mean, what is the mean? Right here, 64 is the mean. And then the standard deviation is 27.5. I'm sorry, 2.75. Now, just to clarify, the lower bound is determined by looking at where you want to find the percentage of, okay? In this problem, the lower bounds, it says between 64 and 65. So this is actually where you look at for your lower bound. And this is your upper bound right here. It just so happens in this problem that the lower bound coincides with the mean, all right? That's not always the case, so you gotta be careful. And then there goes your standard deviation. All right, so just plug this into your calculator and then we'll see what the correct answer is. All right, so you just press second function variable to access your distribution manual, and then distribution, go down to normal cumulative density function, press enter. So remember the syntax, lower bound 64, upper bound is 69.5, the mean here is 64, and the standard deviation is 2.75. Enter. So this is in a decimal form, so 0.477. So our answer is going to be 0.4772, basically 47.72. Well, let me make sure I rounded it correctly. So yeah, okay. Percent. We also rounded to the nearest whole percent, so we are rounding it to the ones place. Look at the number to the right. It's 5 or greater, so we're going to round up. Okay, we're going to carry one over, so it's going to be 48% to the nearest whole percent. That's what we were asked to do. All right. So that's basically the percentage of the population that's represented by this shaded region right here. Answer to number 9 is option number 2. All right, let's take a look at problem number 10. It says the formula below can be used to model which scenario? So we have A1 is 3000 and AN is equal to 0.8 A sub n minus 1. Okay, so we have a recursive formula here. Now, one thing you want to note is how to relate the rate provided with a growth or decay scenario. All right, so let's note the following piece of information. So if you're given an initial amount, okay, and let's say the amount is A1, and you have a rate R, okay, you have a growth scenario when terms are generated if the rate is added to 1 before it's multiplied by the initial term, okay? You have a decay scenario if the rate is subtracted from 1 and then multiplied by the initial term. Okay, so the operation between 1 and the rate should tell you if it's going to be going up or going down. Okay, it's just like growth and decay. You look at the sign before the rate to know if you're growing or you're decaying. All right, so that's what's going to be the telltale sign here. If you notice, I have the signs color coded because that's where we're going to be focusing our attention on. Now we're provided with the recursive definition a1 equals 3000 and an equals 0.8 a sub n minus 1. Now what on earth is going on here? Well, let's find what A2 is. Okay, we'll examine the relationship between A2 and A1 as indicated in this notes. And then we can be able to determine if this is growing or decaying and what rate, and at what rate that's happening at. All right. So A2, using our recursive definition. Okay, so this is A2 is going to be 0.8 times A2 minus 1. Okay, A2 is going to be 0.8 times A1. All right, what is A1? A1 is 3000, so we're going to plug that in. To here, we have A2 is going to be 0.8 times 3000. Now, what on earth is this? Is this a decay or a growth? And by what percent? So this is the rate right here. What we're going to do is we're going to express it as in the format 1 plus r or 1 minus r. So the question is 1 plus what gives you 0.8? That's easy, right? Is 1, I'm sorry, no, I meant to say 1 minus or plus what? In this case is 1 minus. Okay, so A2 is going to be 1 minus what gives you 0.8? 0.2, you can do that with your calculator. So 1 minus 0.2 times 3000 is equal to this right here. Now, just take a look at this format for a second. All right, now let's compare it to the formula we had written above. A2 is 1 minus r times A1. What did we say this was? Was it growth or decay? This is decay because you have a minus here, okay? And the rate is what? 0.2 or 20%. So what's happening is that A2 is going to be 20% less than A1, okay? A3 is going to be what? A3 is going to be 20% less than A2. So it's like that percentage of decrement, that decay rate just continues. And it's less because it's minus. Had it been this where 1.2, guess what? That would be an increment of 20% every year. Okay, so with that in mind, let's look at the options that we have right here. If you zoom down to option number 4, it says the initial value of the specialty toy is 3000. So A1, the initial value is 3000, and its value each of the following years is 20% less. That's exactly what you're looking for because of that minus. So the answer for option number 10 is number 4. All right, so let's go over 1, 2, and 3 to see why those are not the correct answers. Okay, so for option 1, it says the first row of a stadium has 3,000 seats, and each row thereafter is 80 more seats than the row in front of it. This more alone is a dead giveaway. We're looking at a decay scenario, so we're looking for less. Option 2, the last row of the stadium has 3,000 seats. Each row before it has 80 fewer seats than the row behind it. This is fewer, which is good, but what is this? This is an amount. We're looking at a rate, okay? And the decay rate here is 20%, 20% decay rate, okay? So either it's 20% less or it's 80% off the original row, okay? So neither of those cases are applicable here, so that cannot be the answer. Option 3, a bank account starts with a deposit of 3,000 and each year it grows by 80%. See this right here? That's absolutely wrong. It's the wrong direction and the rate is also wrong. What's happening here is a decay of 20% or 20% less than the initial. So that is why option number 3 is incorrect, okay? Thanks so much for taking the time to watch this presentation. I really appreciate it. If you found the contents of this tutorial helpful in your preparation for your upcoming Algebra 2 Common Core Regents exam, do give us a thumbs up. Your positive feedback is very important and supportive to us. Questions and comments can be included in the comment section below, and we'll be glad to provide you with support. Do not forget to subscribe to our channel so you can get updates to the remainder of this review series and other cool math tutorials. More clips can be found on math.serve.com. Thanks again for watching and have a wonderful day. Goodbye.